Hi, everyone. This is Jeff Wu, and I'm going to talk about the interconnect, electromagnetic interference, physical mechanism, and prevention for the ECE571 Project 1. Here is the outline for this presentation. First, I will go through the definition and types of EMI, and then we'll talk about the impact of EMI on integrated circuits. Then I will discuss on the EMI modeling techniques, including capacitive coupling, inductive coupling, and then modeling method by machine learning. Then I will talk about the EMI prevention techniques, including literature that proposes adding absorbing materials to the circuit. And the second is on an example of a circuit design that alleviates the effect of the EMI. Finally, I will talk about the optical interconnect that can be used as an alternative to the traditional integrated circuits that completely eliminates the EMI noise. Finally, I will offer a conclusion. So definition and types of EMI. Electromagnetic interference is a disruption generated by an external source that will affect the operation of a circuit. And then EMI includes conduction coupling, radiation coupling, capacitive coupling, and inductive coupling. So for the radiation coupling, it's done via the microwave wirelessly, and then the rest are through the capacitive coupling and inductive coupling are also through the EM waves. Mostly it's contactless. And then the impact of EMI on integrated circuits. So first, it will cause functional failure in the circuit. When the EMI noise exceeds the noise margin in the digital circuit, it will cause the logic to flip and then causing some functional failure. Secondly, it will cause delay uncertainty, and thirdly, it will cause glitch power consumption. So basically, because of those ringing effect and resonance, the glitches will have extra power consumption. Next, I will go into the capacitive coupling. So in this paper, capacitive coupling noise is characterized in a closed form expression that include the peak amplitude, pulse widths, and time domain waveform of the crosstalk noise. So the background is that there has been a classic model called the Devgan's metric for crosstalk noise estimation. But the issue with this method is that the time constants of the exponentially rising portions of the victim node when it's comparable or larger than the input rise time, the noise estimation is not accurate. So here shows an example of a Devgan's metric. Basically, the two capacitive coupled wires are considered as transmission lines, shown on the plot to the right. And then through long derivation the crosstalk voltage can be derived as shown to the formula in the on the left. So basically, it's a ratio of the CC divided by CC plus C total, which is the C total is a CD2 plus C line 2 plus CG2, basically all the added capacitance. And then there's a time decaying constant here that is also dependent on the circuit itself. So the UT denotes the input response or step input. So the effect of the rising time of the step input is shown on this graph. We can see that basically for a crosstalk, so for a flattened ramp input, the crosstalk is lower in voltage, but longer in time, while the crosstalk for step input is much steeper and immediate, and with a higher peak, and then decays faster. So the model of this proposed by this paper aims to close the gap between the true response and the model or analytical expression output. And the maximum error of the models is less than 13%. An average error is 5.8%. Here is a closed form expression for the crosstalk voltage. So I will not dig into the details of the derivation, but the big idea is that the authors modified the Elmore delay model and include some additional modeling for the time constant, and that basically responds to that slow varying input step. And then the simulation results show that basically the diamond shaped curve proposed by the new methods is closer to the true H-spice simulation, while the Defgens model is far away from the result when the input rise time is low. So basically, when the input rise time is low and then the input rises very fast, the models from Defgen are not accurate, while this derivation offers a more accurate result. Next, I will go into the inductive coupling. So one key difference between inductive and capacitive coupling is that inductive coupling is caused by long-range magnetic fields, while capacitive coupling is caused by local electric fields. So normally when people want to reduce the capacitive coupling, they would increase the distance between interconnects. Then at the same time, inductive coupling would dominate the effect, the EMI effect. Because this slide shows the modeling of inductive coupling. So basically, on the plot to the left, it includes no inductive coupling, and we can see that the curve is very smooth. With the modeling of inductive coupling, in both the shielded and unshielded example, there are more ringing and ripples on the plot. So basically, with inductive coupling modeled, system exhibits significant ringing. Next, I will talk about another literature that offers a new machine learning based modeling technique for signal integrity. So the idea is that EMI simulation is computationally expensive. The main types of simulation techniques include EM solvers and circuit simulators. And shown on the right is a eye diagram that is commonly used for signal integrity analysis, and the eye height and eye widths of particular interest. Here is the topology that are used in this paper for characterization. So we can see that it consists of a transmitter chip and a receiver chip connected by the PCB. Shown on the right is a table of the design parameters. So for the transmitter and receiver, it consists of the jitter, while the interconnect part, it consists of the trace width and spacing, dielectric constant, substrate thickness, loss tangent. Then a deep neural network is applied to train from prior data to model the those design parameters to predict for eye height and eye widths. So it turns out that the learning-based approach requires no substantial domain knowledge and produces good result. It basically saves the complex and expensive circuit simulations, and the plot on the right shows different training result for prediction of the eye height with different kernels in the machine learning. And next, I will talk about the EMI prevention techniques. So this slide summarizes the main techniques for EMI prevention. The first that comes into mind is the use of shield or absorbing materials, as I will talk about later. So the idea is to block the field with barriers made of conductive or magnetic materials. The second method is by conventional grounding of PCBs. We can take a look at the plot on the bottom right. So basically, the dedicated ground planes are placed so that the wires are isolated from the rest of the circuit. The third way is by moving victims further away from the radiation source for the attacker. The fourth way is to use bypass or decoupling capacitors whenever possible for those active devices, and then decouple with a supply. The fifth way is by using differential signaling, and it's great to reduce the differential mode noise. And also people can improve on circuit topology so that the circuit is designed to be immune to the EMI noise when they are modeled as an input referred noise. And finally, people are exploring the alternative of optical interconnects and it's used in the CMOS circuit. For shielding in VSI, we can see on the top right plot, the principle is that the incident noise will come to the shield and it gets reflected. And the attenuated noise will go through to further somehow affect the circuit, but not as strong as it will be without the shield. And a good example is a Faraday's cage. Basically, when one stands in an elevator or in a metal cage, the EM waves coming from the outside would be hard to get in. So this is the same principle. And for the two graphs to the bottom, we can see that in the typical VSI layout, when the wires are compact and close to each other, we can add the in the right diagram, we can see by adding VDD and ground lines, the shield is effectively created. Then we talk about the absorbing materials, which serve as an alternative to the metal shields. So this paper proposes adding absorbing material to a connector or socket to suppress the EMI noise in high-speed interconnects. So it mostly deals with examples that or situations where switching noise of the voltage regulator causes EMI issues due to the radiation or packages to generate the power noises. Advantages of the absorbing materials include the easiness of manufacturing and low cost. And they are also better than metal shielding in suppressing the noises caused by stop resonance or impedance discontinuity. And there is no aggregate resonance or noise coupling at high frequencies. So the latter two are drawbacks of normal metal shielding, or just shielding by normal metal wires. These three pictures show an inductor with the absorbing materials surrounded. So on the original DIMM connector, absorber is added to the bottom, as shown in the middle graph, and then to the inside wall of the slot of the ground pin, as shown to the right. Another component that is made from this principle is an inductor surrounded by the absorbing materials, such that it will not be coupled to the rest of the circuit when used in the circuit. The simulation results show that the EMI-induced resonances are greatly attenuated by the absorber materials. We can see that on the left, there are multiple places where the resonances occur. This is the original connector with no absorbing materials. And with the absorbers added, we can see the two plots show that they are much smoother and the ringing effects are greatly attenuated. Similarly, for a step response, with the original connector, the ringing intersymbol interference and noise are causing the signal to oscillate. And then by adding the absorbers, we can see that the step response after a certain time goes much stable than without the shield or without the absorbing materials. Next, I will briefly talk about an example that applies the EMI considerations that basically improves the circuit topology so that it reduces the EMI referred noise. The idea is when an EMI signal is present at the input terminal of the op-amp, it will introduce a DC offset voltage at the output called the EMI-induced output offset voltage. And it turns out that the proposed new structure or topology achieves 4.6 millivolt from 1 megahertz to 1 gigahertz input offset voltage, much lower than the classical Miller op-amp. These are the comparison of the classical Miller op-amp and the robust Miller op-amp. The new topology has a much less output offset voltage induced by the input EMI noise. Shown on the left is a plot that compares a Miller op-amp and the compact Miller op-amp with RS response. We can see that as frequency goes to the 1 gigahertz range, the traditional Miller op-amp output offset voltage shoots up, while the new topology is relatively constant. On the right table, it's showing a comparison of different topologies. And finally, I want to mention the optical interconnect as an alternative to traditional interconnects. From the table to the right, we'll observe the trends in CMOS-based systems that the local wiring pitch are going down, the chip size is maintained at a constant level, and then total interconnect length goes up almost exponentially, so faster than linear fashion. So the optical solutions arises as two ways. One is called interchip, and the other is intrachip. So interchip is now relatively mature, and it offers greater connectivity for parallel computing through the optical I/O pads and wavelength division multiplexing, while the intrachip one is more challenging and still requires more design methods. The advantages of optical interconnects include the increasing bandwidth and the immunity to EMI noise, and the decrease in power consumption and the immunity to temperature variations. This slide shows two fabricated hybrid interconnect. So basically the design of hybrid interconnect of CMOS and photonics is non-trivial. Photonics are not used yet as memory or logic devices. Those are still processed by traditional CMOS process. And then photonics is introduced to only replace the interconnect. So on this slide, we can see that how a photonic driver and receiver operate in a hybrid system. The photodiode basically are driven to transmit the signal, And on the other end, we have the receiver circuit. That also has a photodiode that is then converted into voltage or current signals through transimpedance amplifiers and comparators for data recovery. And this slide shows an example of optical H-tree clock distribution network. We can still see that the electrical clock trees are still there, while the optical waveguide is added to resolve the latency between the clock delivery. And there are optical receivers at each end of each unit of this tree. So conclusion, we went through the impact of EMI noise in integrated circuits, and we discussed about the modeling of EMI and in an analytical way for capacitive and inductive coupling. And also I introduced a machine learning based data-driven way to model the signal integrity issues. And finally, I introduced EMI prevention techniques, including proper circuit design and optical interconnects. So all the addition of shielding and decaps and new circuit topology all fall into the proper circuit design category, because I believe it's mostly considered as an extra constraint in circuit design phase. And that summarizes my presentation. Thank you for listening.